So far, observationally, we have observed about 30 TDE candidates. I think I don't need to go through them with you again. In the later session today, you're going to hear about soft X-ray TDEs. These are the earliest detected TDE candidates. There's interesting UV optical TDEs and their lamp profiles. We have observed TDEs in hard X-ray gamma ray from the jetted events, and also radio signals have been detected with both the jetted and non-jetted events. And also ongoing and upcoming emissions are going to boost the sample size up to by a factor of 100. So with a lot of upcoming spectral emission profiles, the key question is, in my mind is, are we seeing the same type of beasts? Are they different beasts, or are we seeing the same elephant, but we are blind people touching different parts of it and we think they're different beasts? So in my talk today, I'm going to focus on the soft X-ray TDEs because I'm a theorist and I like cleaner things. And I think soft X-ray TDEs are cleaner. They must be from the accretion disk. Well, for the optical UV TDEs, they could be from the disk or the reprocessing of the photosphere. They could be from the circularization energy. It's less clear to me what is going on with them. So before I start my theoretical talk, I would like to show you a very nice figure plotted by Stone and Metzger, and here is some distribution of a bunch of TDE samples. And it seems to me the UV optical, I'm sure he's going to talk about this more tomorrow on Thursday. It seems the UV optical TDEs are more concentrated around black holes of mass a bit less than 10 to the 7 solar masses. And the X-ray gamma ray TDEs seem to have a flatter distribution with a little bump around 10 to the 6 solar mass black holes and another little bump around the very massive black holes. So for the soft X-ray TDEs, I'm going to talk about these are not the jetted ones. And the black body temperature, as listed here, is mostly between 10 to the 5th to 10 to the 6th kelvins. So why X-ray temperature for these disks? So if you ask people like Martin Rees 20 years ago, and he would tell you, oh, all the TDEs should be in soft X-ray temperature. And as you have heard many times in the previous talks, the reason is very, very simple. In these old pictures, the circulation is thought to be magically happening around the pericenter, and you form a very small disk. So for this very small disk, it is not just the thin flow time scale is very short. So the accretion rate and the light curve would trace the fallback rate. But also, because the fallback rate for most of the systems are super Eddington, if the black hole mass is not bigger than roughly 50 million solar masses, then the accretion rate is also super Eddington. And if you distribute Eddington power across this small photosphere or across this small disk, you get a black body temperature which is peaked in the X-ray. And of course, as you have heard in the wonderful talks yesterday and this morning, the circulation turns out to be rather inefficient, either through the nodal shock of the pericenter passages of the stream or through stream-stream collision and caused by the apsido GR precession and the energy loss through that. So what does that mean? That means the disk will take some time to form. The simulation of parabolic TDE suggests the disk could be rather extended, and the accretion rate could be 10 times or even less than the peak of the fallback rate. So if that's the case, it seems rather hard to produce a very luminous X-ray flare as we have observed in some of the TDEs. So I was thinking about this problem. I was playing with the parameters to see if there's a way of recover the classical picture. And I found the key thing to recover this classical picture is to have a high accretion rate and a small photosphere. And the magic I found is to have deep plunging stellar orbits or high beta stellar orbits. And what is a high beta orbit? So let me remind you again, what is beta? Beta is the penetration parameter. It is defined by the tidal radius divided by the pericenter distance. So for fixed star black hole disruption, RT is fixed, but you can always vary RP so the star can penetrate through deeper and deeper into the potential well of the black hole. And when beta is bigger, that means the orbit is closer to the black hole and the stream is affected more by the gravitational effects, affected more by the GR effects. So what's the difference between a low beta and high beta encounter? They would matter for, as I'm going to show you in the talk, they will matter how fast synchronization happens, where the synchronization happen, and also what is the eventual size of the accretion disk and temperature. So here is some simple illustration of a fiducial setup of a tidal disruption event using a solar type star disrupted by a 1 million solar mass black hole on a beta equals 1 orbit. The star comes in a parabolic orbit, is disrupted here. A while after disruption, the tidal stream is rather elongated. So most of the earlier tidal falling back materials is going to be along this most bound orbit. And from the parameters of the mass ratios and stellar orbit, we know the size and eccentricity of this orbit. After the head of the tidal stream falls back and passes very close by the black hole, it gets some GR absolute precession and is deflected on the way out and is going to collide with the trailing part of the tidal stream. And that is why you see the collisions in all these wonderful GR simulations, as people have shown yesterday. And you know what is the precession angle over one orbit from GR, which depends on the size and eccentricity of this ellipse. And for this setup, you would see actually the tidal radius is at roughly 50 Rg, so the absolute precession is weak, and the intersection happens rather far away, close to the epicenter of this most bound orbit. So keeping the other parameters the same, but if we just increase the beta parameter to be a larger value, and you will find the absolute precession angle is bigger, and the tidal streams intersect much closer to the black hole. And here I'm just showing this plot. This is the same setup as in Shirakawa's simulation, the disruption of a white dwarf by an intermediate mass black hole. To show you, in this situation, in this simulation, the absolute precession is also rather weak. So this is closer to this simulation, to this situation, rather than this situation. And also, we can find what is the interception radius and the collision angle when the two streams collide. And they turn out to be rather simple equations of like the eccentricity and other quantities, which are basically, they're just functions of the mass ratio of the star and the black hole, and also the beta parameter of the stellar orbit. And here I'm plotting the interception radius in gravitational units, and the x-axis is the mass of the supermassive black hole. And the black curve is for the beta equals 1 encounters. And this is for higher and higher beta encounters. And as you can see, and it's the same with your intuition, if the beta keep the same mass but increase the beta, then you would find the intersection radius of the stream gets closer and closer to the black hole. And similarly, we can plot for the collision angle. Why do we need to know this? Because the energy loss when the two streams collide and how fast the synchronization happens would depend on these two quantities. So what is the energy loss at the tidal stream intersection? So we assumed a very simple assumptions without doing any hydro simulations. We assume that outgoing stream and the incoming stream have similar momentum, and also the collision is totally inelastic. And of course, this is upper limit of the estimate of the energy loss. So this is saying after collision, the two streams merge and they move at the same speed. And as you can have seen from the simulations, or in actually the reality, like there will be lots of more complicated things going on. There will be mixing of materials, deflection of the tidal stream, shocks generated, and redistribution of angular momentum, lots of things going on there. And also for these high beta encounters, as for example, you have seen in Claremont simulations, you see the tidal stream could go through each other for several times until they finally settle onto like one stream. So my interpretation of this energy loss is, so the energy loss must be a function of the collision speed, and the higher the collision speed is, the more energy loss there will be. And it should also be a function of the collision angle, And the bigger the collision angle, the more the energy loss is in the stream collisions. So you should take this as an order of magnitude estimate of how much energy is lost. And it is not necessarily the energy lost in the first intersection. It's more or less like after several intersections, when things relatively settle into one stream, this is the total energy loss. And also we can calculate what is the stream with the collision speed of the tidal streams from where the intersection radius is. And for hybrid encounters, they intersect much closer, so the speed here is higher. That's why the energy loss here is much bigger than here. So from the energy loss in the tidal stream, we can estimate the size of this elliptical accretion disk formed after collisions, which is the initial phase of the disk. And for hybrid encounters, the size of the disk has a very simple relationship with the intersection radius and also the collision angle. Okay, so plotting the size of this elliptical disk. Y-axis is the size in gravitational unit, x-axis is the mass of the black hole, and similarly for different beta encounters. And actually, the size of the disk behaves rather similarly to the interception radius. So the bigger beta is, for the same black hole mass, the smaller elliptical disk it forms. And here I also plotted in dashed line the classical circularization radius, which is 2rp, which is assuming the angular momentum is conserved in the circularization radius, circularization process. And you can see actually for high beta encounters, or like very big mass black holes, the elliptical disk size is not that big compared with the classical radius, the classical circularization radius. This means they are more or less circularized, or they can circularize very fast. And for these low beta encounters, especially here, it seems the disk is still extremely elliptical. So I'm not certain what is going to happen here. Perhaps this is going to be Jerusalem bagel model, or perhaps there's some circularization is needed before the thing, most of the thing accrete onto the black hole. It is possible that this can retain some elliptical configuration while accrete onto the black hole, or full circulation may never happen. So we are still waiting to see a hydrodynamical simulation on this to confirm. Okay, and if we plot the number of collisions needed, basically not just by naively taking the total energy the stream needs to loss to go into full circularization divided by the energy loss in the collision each time. This is roughly the number of collisions it takes. And again, this is only an order of magnitude estimate. What I will take from this figure is it's telling us like in which regime what physics is going on. So I would say within, like below the blue line, the circularization is going to happen very fast, and above that is going to be slow, unless some magic things can happen. And also to the left of this purple reddish line is going to be in the super-Eddington regime, and to the right of it is in the sub-Eddington regime. So for example, for 10 to the 5th solar mass black holes, no matter how slow the circularization is, the accretion is going to be in the super-Eddington regime. For things like a few times 10 to the 6 to 10 to the 7, it depends on the beta parameter. And for very massive black holes beyond 10 to the 7 solar masses, everything is sub-Eddington, even if the circularization happens very, very fast. Okay, so the X-ray TDEs model I'm going to talk about is mainly in this regime for the high beta encounters, and there are super-Eddington TDE accretion systems. So how much do we know about super-Eddington accretion flow? Not until very recently people have started to do simulations to understand them better. So for example, one of the experts on this is Oleg Sadowski. In their simulation done this year, they have found in the super-Eddington accretion disk, and these are very large extended disks, not necessarily TDE disks. The disk is very thick, extremely thick, both geometrically and optically. And also a lot of outflow is generated on the surface of the disk. And these outflows are completely optical thick, and they are very extended in opening angle. So this means the inner part of the disk is going to be obscured. You're not seeing through something here, but only the outer part of the disk, or the photosphere, or the outflow. And also in another super Eddington simulation done by our group, geometry simulation with a jet trigger, we find similar results, but also the photosphere would have a viewing angle dependence because the jet would change the configuration of the photosphere. And what is the luminosity in these super Eddington systems? As Roseanne talked about yesterday, there is still a debate by various groups, but it seems that the luminosity is thought to be either around Eddington or slightly above Eddington, if there's no jet. Okay, so if we adopt the results from those super Eddington simulations and apply them onto TDE accretion disks, what do we think we know about these disks? So the disk is very small compared with the AGN disk. It is going to be optically thick and geometrically thick. I did a calculation with the outflow. I found it to be optically thick close by, and the optical depth is going to be less than 1 beyond the size of the disk if it has a very extended opening angle. So that means the photosphere of this system is going to be roughly the size of the small disk. And inside the photosphere, we are probably not seeing through the most inner region of the disk. So that is why the temperature we see is going to be the surface temperature of this photosphere. And we can calculate this temperature by setting the luminosity of the system to be kept by the Eddington luminosity if the accretion rate goes beyond the Eddington accretion rate. And we can plot the effective temperature using this relationship. But before that, I want to point out for these high beta super Eddington accretion systems, everything is going to be obscured by this photosphere with Eddington luminosity. So either the accretion power or the circularization power is beyond the Eddington luminosity. So, but then if everything is obscured, there is no way of telling where the power is coming from. Okay, so showing a bigger figure of the temperature of these events. The y-axis is the temperature and the x-axis is the black hole mass. The color scheme is the same. So for example, for the beta equals 1 encounter, we find the temperature increases first with the black hole mass and then eventually decrease when it goes to very high. And also for the same black hole mass, of course, if we increase the beta, then the photosphere size is smaller, then temperature of that photosphere is higher. If we draw some division between X-ray events and UV optical events to be here, then we will find the X-ray events favor high beta cases, beta roughly bigger than 3, and also black hole mass on the small side, less than 5 million solar masses. Okay, so we think that could be responsible for the bump here. But as you see from this figure, there is also a bump on the very massive side. What are those X-ray TDEs? So it turns out these ones are even easier to explain. So in the 10 to the 8th, for 10 to the 8th black hole masses, the fallback rate here is sub-Eddington. So the accretion rate must also be sub-Eddington. So that means the accretion disk is no longer super Eddington thick disk. It goes back to the standard Sakura's NEF thin accretion disk. And there is some wiggling room of the mass estimate here. But for very massive black holes, they would favor a spinning black hole case actually for stars to be disrupted outside the event horizon before plunging into it. And also, these events must happen very close to the black hole, so GR is dominating the dynamics there, because the tidal disruption radius divided by the gravitational radii is actually a negative parallel function of the black hole mass. So for 10 to the 8 solar mass black holes, everything happens within the tidal disruption happens within 10 gravitational radii. And that's why the GR absolute precession must be very strong even for low beta encounters here. And the tidal stream intersection is also happening very close to here, to the event horizon. So circularization must be really fast. And also for this Sakura's NEF thin disk, there is actually not much room for it to grow beyond. So the intersection radius is within 10 gravitational radii, and also the ISCO is varying between like 1 and 9 gravitational radii depending on the spin. So this disk is really, really very, very small, and therefore the temperature of this thin disk is basically the same as the ISCO temperature. And if you remember, the ISCO temperature for for 10 to the 8 solar mass black hole is actually in soft X-ray. Okay, so that's the main message of my talk. The circularization speed, where the intersection depending on where the intersection happens, and this depends on the beta and the mass of the black hole. The mass accretion rate is more sensitive to when you vary the beta parameter than the mass of the black hole. And there seems to be two ways of producing soft X-ray temperature TDEs. One is for TDEs happening on the smaller side of the mass disk spectrum. These are super Eddington high beta encounter events. And on the very massive side, these are just very small thin disks with the ISCO temperature in soft X-ray. So that's my talk. Thanks. Mm-hmm. This is not actually, this is interesting. That's a good question. Yeah, I can repeat the, yeah, sure. So he is asking about this turning point. So, I mean, so first here, like, here we are assuming, we're just taking the black holes to be non-spinning. If you have a spin, like, of course, this would not be that accurate, but this is actually because of the collision angle. Yeah. I think even you're right. Yeah, the energy loss could. Yeah, but I mean, you shouldn't trust things too much here, basically. Yeah.
Can you comment about the rate specifically? So at the low mass you require beta 3 soft X-ray.
Mm-hmm. Yeah, that's a very good question. What is the rate of these high beta encounters? They are going to be low compared with like low beta events or partial disruption events for sure. I mean, it depends on the full loss cone or empty loss cone scenario. In one case, the probability of having like less than beta, bigger than beta encounter goes as 1 over beta, and the other one goes as 1 over beta square. I forgot which one is which. But so the high beta ones are going to be small, but the sample of X-ray TDEs we have is also small compared with the optical TDEs.
In regard to the high mass cases where there's sub-Eddington by a little, why wouldn't the continuum spectrum look basically like a quasar, except that it's cut off at long wavelengths because the disk doesn't extend out very far? And quasars don't peak from soft X-ray.
Do we know where the X-rays in quasars come from? I mean, maybe they're from corona.
Well, the typical story in quasars is indeed people attribute, and I think it's pretty good reason, attribute the hard X-rays to a corona. But that's not the majority of the light. In nu L nu terms, they pretty generically peak in the ultraviolet.
It's a reflection.
No one knows why, but empirically we see it.
Nothing when there is like spinning it from its maximum speed, then you can get it a little bit case of the temperature.
Not going to gain you much.
I mean, there's reflection reprocessing. It flares up a little bit and it intercepts some of the light from the inside. That's been the explanation. There's a debate whether it's actually reprocessing of the light or if it's just solely.
That's
getting the field, that doesn't change the peak.
Yeah,
You're looking at it.
right.
They're getting the big blue blob.
Yeah, but it doesn't change the peak of the emission.
Well, I mean, there's two peaks. There's this big blue blob and then there's the soft X-ray. And the big blue blob is higher.
James, there's no empirical evidence for a soft X-ray. And the usual reprocessing story has to do with coordinating fluctuations along the wavelength. But those are still a minority of the light.
take this with a grain of salt. All of these masses were taken from galaxy scaling relations, which have some uncertainty scatter in them. That's why this curve has widths rather than it's continuous rather than curious, because there are different errors with the incremental mass measurement. But to put this in the context of circularization, if you take the typical mass of a star drunk through the ion that gets disrupted, which is 0.3 solar masses, that peak at 10 to the 6.8 solar masses corresponds to a pericenter of 8 RG and a beta equals 1 event has a pericenter of 8 RG, and that same beta equals 1 event has a self-intersection radius of 80 to 90 RG.
Mm-hmm.
So those are self-intersections that are quite close.
So you mean this peak?
Yes.
Okay.
If you're looking at a typical low mass star getting disrupted, so I think that does correspond to self-intersections that are happening pretty close to the black hole.
Sure. I mean, it is possible, like there's some reprocessing going on, and that's changing some of the X-ray into optical. That's definitely not accounted for in my model. Like I just have this X-ray emission black body surface, but it could be a viewing angle dependent thing. It could also be reprocessing. So we can talk about that later.
Okay, I think we should stop here. I think you should appreciate my success as a chairman. All the speakers